Hi guys, so just some quick notes today, kind of building on what we finished with at the end of last class. Today we're going to be looking at acceleration. So we really focused on speed and velocity and frame of reference last time. Today we're going to be looking at acceleration. Now this is the first time we're getting really into a derived unit. We had speed and velocity are both derived units, but today we're really going to look at uh, the trajectory that we're headed in terms of more and more derived units. And I'll need you to go ahead and make sure you kind of see that as we go ahead and go along. So let's start with our essential questions. Number one, what is acceleration and how is it related to velocity? The fact that I'm asking about velocity should tell you something about acceleration in terms of its properties right away. Number two, how are distance time graphs similar and different to velocity time graphs? Notice we're changing out one of our units here from distance to velocity. And I want you to be specific as you go through this so that you can tell me about what these two graphs show and how they show that. Let's do a really quick review based on what we went over last time. First, let's go ahead and take a look at speed. Speed, as we saw, is the rate of motion or the distance covered per unit time. But remember that this is a scalar quantity because it does not have a direction attached to it. This is different from velocity, which is speed in a given direction. So this is a vector quantity that is not only magnitude, but speed. So in terms of mathematical notation, we can use the same equation. Speed equals distance over time. Remember, velocity equals distance over time by simply adding a direction, making it a vector quantity. We also went over our distance time graphs, and remember that if a line is horizontal, distance is not changing, therefore the individual is not moving, they're stationary. If the line is going at an angle, okay, it's going up or down, this one only shows up, but if it's going down, the object is moving. Now, if it's going away, the object is moving away. If it's coming down, the object is getting closer. Okay. When we look at distance time graphs that have multiple areas, you can see in the first portion of this graph, from 0 to 8 seconds, the individual is moving away at a constant speed. It's a straight line. And during that time, we're going at a rate of about 100 meters for every 4 seconds. It's about 25 meters per second. Then from 8 to 12 seconds, you'll notice that the distance does not change, so the individual or object becomes stationary. And then as we go from 12 to 20 seconds, we're going at a rate pretty straight, not quite perfectly straight, but pretty straight at a rate of about 150 meters for every 4 seconds. Okay, so obviously we've sped up at this point. We're going at a quicker rate, but still constant rate. So we're going to add a little change to this, and that's going to be accelerating. It's not normal that you would go ahead and instantly be at a certain speed, instantly stop, instantly speed up, that sort of thing. And so what we're going to look at is how we get to these differences in speed, and this is known as acceleration. So acceleration is a change in velocity over time. Now, hopefully we can stop and think a little bit about the units that we're dealing with here. Now, when we start thinking about the units, hopefully you remember from last time that we had a derived unit in terms of velocity or speed. And when we look at this unit, it was meters per second. So two base units, meter and second, combined together to make meters per second, showing a relationship that is the derived unit that we had for velocity. Now we're going to do something similar here when we take a look at acceleration. So when we go ahead and take a look at acceleration, we need to think about what units we're dealing with. Now we have velocity, which we just said was in the units of meters per second. Now, delta right here, hopefully you recognize this, this represents change in, okay? So delta equals change. So what we're really looking at is meters per second, and we're looking at a difference in meters per second. So let's go ahead and call this meters per second the unit, but we'll call this V final minus V initial all over the time it took. And usually we go ahead and use time in terms of 0 to some point. Now, it is possible to go ahead and say t final minus t initial, but typically you'll go ahead and see this in the form of vf minus vi over s. Okay. Well, time, okay, is in seconds, and this probably should be time, okay, t. When we look at these units, we have velocity, which is already meters per second. And so we're adding this or dividing this by time. So this ends up being meters per second per second. So the standard unit that we use when we look at acceleration is meters per second squared. Okay, because when we do this in terms of division, if we go ahead and do meters per second, this is going to be divided by seconds. You'll notice the seconds are together, so we can times those together, meters per second squared. And that's the unit that we're going to go ahead and take a look at when we go ahead and take a look at this. All right. So this is going to be a change in speed or a change in direction because, like velocity, it is a vector quantity. And so when we're dealing with vector quantities, we have to realize that direction matters. And so this is important because as you go further, you're going to start to realize that even if you're traveling at the same speed, you can still be accelerating. And this is because you're changing your direction. So if the speedometer in your car, which measures speed and not velocity, is still reading 50 miles per hour, and you go around a curve, you are accelerating even though the speedometer consistently reads 50 miles per hour the entire time around the corner. Because if you were to draw a vector, the direction in which that force or that velocity is going is changing from one moment to the next. And as such, you are seeing a change in direction and a change in velocity because they're vector quantities. Okay, so let's take a quick look at our acceleration in terms of a distance time graph, what we were looking at before last class. The graph to the right here shows change in distance over time, but what you should notice here is it's not a straight line, okay? This is a curved line, so the amount of distance covered per second is increasing, okay? So when you look at this, if you see a curved line on a distance time graph, you know there's an acceleration. Now, what if it's curved the other way? Well, we are slowing down. And so there's still an acceleration, but it's a negative acceleration. And you may often hear the term deceleration, but remember when we talk about deceleration, it's simply a negative acceleration, okay? So you're applying the brakes to your car as you're coming to a stop. This is a deceleration or a negative acceleration. Okay. Straight line is going to mean a consistent speed. And if that is a flat line on a distance time graph, going horizontally, this means that the object or individual is not moving. Another type of graph that we will typically look at when we start looking at these types of relationships is what we would call a speed or velocity time graph. Now, it's easier to call it a speed graph because we don't necessarily have direction on it when we go ahead and take a look at it. So a speed versus time. If you have a horizontal line like you see here on the left, that means the speed is constant. It's staying the same. When you translate that to a distance time graph, it would be an angled line, okay? But it would be straight because you're increasing distance or decreasing distance at a fixed rate. When you look at a speed versus time graph like the one on the right, this is what we call a constant acceleration. And you would see a nice parabolic motion, okay? It's going to curve either up if we're accelerating or curve down if we're decelerating when we're looking at a distance time graph, okay? So there are two types of acceleration. We don't usually use deceleration, although it's all right if you want to use that. Just know that in terms of mathematically calculating it, this is a negative acceleration. When you look at these, if we go up to the right like this, That's a positive acceleration. The object is getting faster. Okay. When you look at the one on the right, this is a negative acceleration. It's going down to the right. So this is an object that is slowing down. Okay. And in fact, on that right one, when you get to the 20-second mark, it's got a speed of 0, so it actually becomes stationary. And so if your time were to continue on at this point, you would actually see a flat line on the distance time graph. All right, so let's do our first acceleration problem. We'll try some simpler ones and then make them a little hard, and then we'll give you some practice when you go ahead and do your lab today. A roller coaster's velocity, remember we're using velocity, okay, at the top of a hill is 10 meters per second. 2 seconds later, it reaches the bottom of the hill with a velocity of 26 meters per second. What is the acceleration of the roller coaster? So let's think about what we know and how we go ahead and do these calculations. First things first, we need to remember that as we go ahead and calculate this, our equation that we go ahead and use is A for acceleration is equal to delta V over T. In this case, we've got V final minus V initial over T for time. I'm always going to ask that you write out what you know and what you don't know and then substitute into your known equations. It says the roller coaster's velocity at the top of the hill, so we're going to call this VI, is 10 meters per second. So VI equals 10 meters per second. 2 seconds later, so that's time, T equals 2 seconds. It reaches the bottom of the hill with a velocity, this is the VF or V final, of 26 meters per second. We then simply substitute these in to our equation and go ahead and solve. So we've got 26 meters per second minus 10 meters per second. And we'll go ahead and solve that first since we've got it set up that way. 26 minus 10 is 16 meters per second. And that takes place over 2 seconds. We go ahead and do our division here. 16 divided by 2 is 8 meters per second, or 8 meters per second squared. Okay, so that's how you go ahead and calculate this. All right, so we can go ahead and clear this off and have the one that I did in the computer so you can see it more easily if it's easier to read. There you go. Acceleration delta V over delta T, 26 meters per second minus 10 meters per second over 2 seconds, 16 meters per second over 2 seconds. Acceleration is 8 meters per second squared. All right, so I want to show you a quick video of a roller coaster ride. And when you finish watching this, I want you to think about this in terms of acceleration, deceleration, and what this might look like on a distance time graph, as well as an acceleration or a speed time graph. Okay, so go ahead and watch this, and then we'll go ahead and move on to the next piece. Go ahead and throw your hands up as you're going through the roller coaster ride if it makes you feel more like you're there. Okay. Okay, so we're climbing here. So we're going up. We're definitely doing distance from the starting point. But are we accelerating at this point? Probably not. Probably going at a pretty consistent velocity. maybe you've been to Six Flags, maybe you've been to Disneyland, been able to go on some roller coasters, you have some idea of what this is going. But notice how high you're getting up off the ground as you look out at the body of water out in front of you.
Is it? Okay, I don't like it. I definitely don't like it. Yeah, at least at 305 you get your ass up there. This is one and done for me. I don't like this at all.
Okay, so we're getting to the top here. So now we're going to see a little acceleration as most of the weight goes over the top. Look at a bank and then a loop-de-loop. And then a deceleration as we come in towards the stop. Cool. All right. So again, remember that acceleration is delta V. So V2 minus V1 or VF minus VI over T for time. Okay. And so make sure that you understand how we get those units of meters per second squared. Let's try another set of practice problems. This time I'm going to let you go ahead and do it, and then we'll go over it. So a car accelerates at a rate of 20 miles per hour per second. How long does it take to reach a speed of 80 miles per hour? Okay. Think about what we know in terms of the equation, and then go ahead and solve this. If you finish that, okay, go ahead and think about these other two questions, and then come back here and we'll go over both of them. A car travels at 60 miles per hour around a curve. Is the car accelerating? Yes or no, and why? And then a car travels in a straight line at 60 miles per hour. Is the car accelerating? Yes or no, and why? Pause the video here and try and solve this problem. Okay, welcome back. I hope you had some time to think about it and get through this. Let's go ahead and set it up and see how we go ahead and do. So what we have here, 20 miles per hour per second, okay, distance per time. This is actually a unit of acceleration, okay? So when we go ahead and write down what we have and what we need, if we think about A equals 20 miles per hour per second, and we're going essentially, if we assume that we go from a VI or initial velocity of 0 miles per hour to a VF of 80 miles per hour, we need to go ahead and solve for time. So I keep doing S today. T equals question mark. That's what we're looking for. Okay. So when we go ahead and set this up, we still have the same equation. We've got A equals VF minus VI over T. In this case, we don't know T, so that's what we're trying to solve. So I'm going to go ahead and use some algebra to go ahead and solve for T. So we're going to go ahead and do T equals VF minus VI over A. Okay. Then we go ahead and simply substitute in t is equal to 80 miles per hour per second. Okay. And when we go ahead and do that, it's minus the initial, which is 0. So I'm just going to leave that off here. Divided by A, which is 20 miles per hour per second. And this one actually shouldn't have the second part on it. Maybe I should just erase that, so it's not confusing. There we go. Okay, so then we simply solve this, and 80 divided by 20 should be pretty obvious. Oops, I'm still on eraser. Should be pretty obvious. This is going to be our t equals 4 seconds. Because notice the second will end up on the top. Miles per hour is going to cancel, and this is where it's very important for you to go ahead and follow your units around. Okay, and if we go ahead and take a look at that, we can see that when I did it before, we got 4 seconds. Nope, I already got the next one coming out too. So if a car travels at 60 miles per hour around a corner, is the car accelerating? Yes. Hopefully you know that this is because acceleration, like velocity, is a vector quantity. And so if you're changing the direction by going around the corner, you're changing the acceleration. And then if a car travels in a straight line, it's not accelerating because we're not changing the velocity and we're not changing the direction. Okay, guys. Thank you so much for your time. I hope this helped you understand how acceleration relates to velocity. Remember, velocity and acceleration are both vector quantities, and they both utilize derived units based on base units. Velocity is a speed with an added direction. Speed is a scalar unit, unlike velocity and acceleration, which are vectors. All right. Have a great one, guys. Take care of yourselves. We'll see you soon. Take care. Bye-bye.